As usual, this session is being recorded live to our Hangouts account, DCG account, and it will be forward link to all of this, so you can rewatch it over and over again. Rachel, would you like to make just a brief presentation while we wait up to the brief house?
No. Yeah, because there are not many things to tell, and if I tell, then you will feel repetition. So, yes, what I'm going to tell is very basic thing. So, but let me ask that: how many of you know about graphs, or like what kind of graphs, or what you have heard of graphs, so that I can keep it very simple or complicated or the presentation.
I heard about graphs.
Yeah. But more than that, you know what is a graph? Okay. Okay. And its relation with architecture or the architecture design.
I'm not an expert.
Even I'm not an expert, but just to know that. Oh, okay. Yes, Professor Dwat told me about that theory. I still have to read about it, but yeah, he told that they use a lot of graph theory. Yeah, so maybe after presentation we can discuss that, how two things are related, or how this work is in particular related to that.
So maybe we can start.
Yeah, because initially they are only definitions, and if someone can come later, so they can join afterwards also. It's not complicated. Should we start? Okay, so I divided this presentation into two parts. One part is general terminology about graphs and how graph theory is relevant to architectural design. The second part is more concerned with my work, that what I have done till far and what I am planning to do. So we start with very basic definitions of graph theory, which are very, very common to architecture. So the graph. So in standard notations, we denote a graph with G, V, and E, where V stands for vertices and E stands for edges, and G is a graph. So vertices are normally the dots, and you connect two dots to draw an edge, and you say that these two vertices are adjacent. So if we say the name V1 and V2, so V1 and V2 are adjacent, and if it is V3, so V1 and V3 are not adjacent. So this is very, very basic thing that the graph is. So it is vertices, edges, and then this thing. Then the other thing is the directed graph, because in this case you can say that V1 is adjacent to V2, but at the same time V2 is adjacent to V1. But if you give some direction, then you can say that V1 is adjacent to V2, but V2 is not adjacent to V1. And the third is the multiple edges, because there can be more than one edge between two. So this thing and this thing. So you can say that there are V1, between V1 and V2 there are three edges. So if we see architecturally, we are not interested mainly in directed edges initially, because if we say that two rooms are adjacent, it means that we suppose that there is a door between them. So if you can go from one room to other, obviously you can come back from that room to this room. So therefore we are not concerned with the directed edges. Same is that we are not concerned with the multiple edges, because normally if two rooms are connected or adjacent, then there is only one way to go and one way to come out. They are not like 3-4 doors and all that. So that's why what we are concerned is that there should not be any directed edges and there should not be any multiple edges. So we call it, if you see the standard terminology, these graphs are called simple undirected graphs. So we always concerned in architectural design with the simple undirected graphs. The other thing is, so now if I am talking about graphs, it means that I am talking about simple undirected graphs only. We are not talking about directed graphs and the multiple edges. The next thing is the connected graphs. So if we see this graph and if I draw one more edge, or maybe I can, so if you see the whole graph together, then this graph is not connected, because from here you cannot reach to the vertices of this part. So we say that a graph is connected if from every vertex of the graph we can reach to the every other vertex of the graph, or there is a path between each pair of the vertices. So again, in architectural design we usually consider the connected graph. We don't work with the disconnected graphs. The next is a tree. Or a cycle. So in a graph, every closed path is called a cycle. For example, yeah, it's not working. So for example, if I draw some graph like this, so this is a cycle of length 4, because there are 4 edges and we start from here and we can end up here. So it's a closed path. Similarly, it is a cycle of length 3, because again it is closed, and there is no cycle. So cycle is a closed path. And if a graph doesn't have any cycle, we call it a tree. So for example, something like this. So this is a tree because it doesn't have any cycle. The next thing which is very commonly used in the papers related to the graph theory and architecture is adjacency matrix. So suppose we have a graph something like this. So A, B, C and D. So corresponding to this matrix, corresponding to this graph, we can construct a matrix where we have the number of rows equal to the number of vertices. So the same A, B, C, D, and here also same A, B, C, D. And we say that we see each pair of the vertices. So we say that A is not adjacent to A, so we put 0. A is adjacent to B, so we put 1. A is not adjacent to C, so we put 0. And A is not adjacent to D, so we put 0. Something like this. So we can construct an adjacency matrix. If you see directly, then you see that it's not very interesting or important matrix, but to study about the graphs, and more importantly, if you are dealing with the graphs, and if you have to write a computer program, then you cannot give input as this graph. It is very complicated, but you can always give input in the form of a matrix. So in that case, this matrix is very important. The next is the weighted graphs, because here we are saying that if they are adjacent, then we put the number 1, otherwise 0. But you can also give weights to the graph. For example, 8, 6, 10, and 9. This weight can represent anything. For example, in architecture, it can represent the distance between rooms. So between C and D, the distance is 10. Between B and C, the distance is 8, and something like this. So you can always associate the weights with the graph, and then according to that, you can obtain a weighted adjacency matrix. One of the most important concept of the graph theory which is used in architectural design is planar graphs. So it means that if we can manage to draw a graph without edge crossing on a plane, we call it a planar graph. For example, if we see the first figure, so there is two edges are crossing at a point, but the same graph can be drawn without edge crossing. If you see the second graph, they both are same. There is no difference. If you see the relation between, they both have the 5 vertices. They have the same connections between edges. The only thing is that the way they are drawn. So in the first case, there is an edge crossing, but in the second case, there is no edge crossing. So if we have given a graph, and if we manage to draw it on a plane without edge crossing, then we call it a planar graph. Otherwise, it's a non-planar graph. Now, if you see the design or the floor plan of any building, and single story, not the multi-story, but the single story, the graph would always be planar, because the floor plan is always planar. They don't cross each other. So that's why while considering the graphs or while considering the adjacency relation, we always need simple, undirected, connected planar graphs. So we start with simple, undirected, connected planar graphs. Like the last graph, we call it a complete graph K5. You can try the way you want, but it is non-planar. You won't be managed to draw it, or you won't be managed to draw it without any edge crossing. So some graphs are planar, some are non-planar. So if like, okay, we'll talk about it. So this is what I'm talking about: simple, undirected, connected planar graphs. This is how we define the adjacency between rooms, because in vertices it's very simple. If there is an edge between two vertices, we say that they are adjacent. But in case of rooms, we say that two rooms are adjacent if they share a part of the wall, or if they share a complete wall. If they touch at a point, then we don't say that they are adjacent, and similarly here they are disconnected. So adjacency means we are taking into account that at least some part of the wall should be shared, so that we can insert a door between the two rooms. So this is how we prefer to define adjacency between rooms. So initially the architectural meaning of the graph. So the first important point is that if you want to give the adjacency relations between rooms, like there is a user or an architect who wants some requirement that, okay, I need 5 rooms, and I want room 1 should be adjacent to room 3, 3 to 5, 2 to 4, then how to present it? So the simplest way to represent that adjacency requirement is through graph. So if you have to give the input, the best way is to give through the graph. And once you have the floor plan, then again, to understand the different connections between the rooms, you can draw a graph for that floor plan or corresponding to that floor plan, so that you can understand that what is the flow of the circulations in the building and how they are connected and what is the distance between these two rooms. So somehow they are connected both the ways. So initially the input, also through input you can get a floor plan, and for the floor plan you can obtain a graph which you can study to understand the different relation between the rooms. Also it gives you an idea of the positions of the doors, positions of the windows, circulation path, and many more properties. So we will discuss them in detail. So if we look at the problem of the floor plan design, normally we have the topological constraints which are concerned with the adjacency relations between the rooms, the dimensional constraints, so the area of the room, the area of the floor plan, and these kind of the things. And then you can add as many as you want, different constraints like the daylight or view. And so if you see the architecture problem, it is a multi-constraint problem. So in this presentation, we are only concerned with the topological constraints. So this is kind of a standard format of a problem which is given by an architect or by a user. So he says that we have the 5 rooms. So we have this graph A, B, C, D, and E. So this graph represents the adjacency relations between the room. So the idea is that we want a floor plan which should satisfy these requirements. This is the most simple problem. So if we see that on the left hand side we have this graph, and corresponding to this graph we have 2 different floor plans, and you can see that both the floor plans are satisfying these adjacency requirements. And then corresponding to these floor plans, again we can draw a graph. So if you see this problem, it doesn't look complicated. If someone asks for okay, I have these 5 rooms, I want this adjacency relation, and can you draw a floor plan for me? So obviously you take a pen and paper and you start drawing something, and at the end of the day you may have some solution or some floor plan. But let's see this problem in a bigger format. Suppose there are 100 rooms. So what you do? You cannot spend the whole day drawing and then keep checking it and then asking others that is it the feasible solution or not. So the first thing is that the feasibility of the constraint. If I give you a graph, how come you know that there exists a floor plan for it or not? Maybe the graph which I am asking is already over constrained and it is not possible to have a floor plan for it, and we spend maybe 1 month to keep looking for the floor plan. At the end of the day there is no floor plan. So this is like typically a mathematical problem that if there is a graph, so does there exist a floor plan corresponding to it, to check the feasibility of the constraint. Now if the same thing, that if we have given the graph, so does a floor plan exist corresponding to it or not? So we need to give some mathematical theorems or some mathematical results which says that yes, if input is this, then there exists a floor plan corresponding to it, otherwise not. The other more complicated thing is that if somehow we have this feasibility constraint, that we know that okay, the constraints are feasible, then you need to design or you need to propose an algorithm which take the graph and then which construct the floor plan corresponding to it. And even if we make the problem more complicated, then we can ask for the shape of the floor plan, because you have a graph which is planar graph, but I can say that I want a floor plan rectangular, or I want a floor plan plus shape, or I want a floor plan L shape. So first thing is that you need to check that the constraint which they have given are feasible or not. If they are feasible, then you need to construct a floor plan corresponding to it into the required shape. And if you have to do this automatically, then you have to propose an algorithm which take the input and propose the required output. So if you see in that way, the problem is very, very complicated. And if the number is big like 1000, or if you have to generalize the results, then it is very, very complicated. And the last thing which many people are work over is that you have given a graph, then which shape best fit the constraint. Like for a given graph, someone can say that rectangular is the best option for it, and maybe rectangular is not satisfying these constraints, so maybe L shape is best, or maybe a plus shape is best, or maybe some other shape is best. So to look for the shape which perfectly, or which best, or which is the optimal solution for the given constraint. And if I'm telling a lot of problems related to this, and if the graph is over constrained, then again we may need to propose an algorithm which says that okay, here are the 20 rooms, 45 edges, but if we delete these 3 edges, then graph won't be over constrained, and then you can have a solution for it. So again we need to develop an algorithm, or we need to propose an optimal solution which says that yeah, the minimum number of the edges which we need to delete, after that the graph or the solution is feasible.
You're always talking about rectangular rooms.
Yeah, rooms in a standard way we take rectangulars. Yeah, because in architecture initially we start with the rectangular, but you know that's the best part of the rectangles. You start with the rectangular, and suppose you don't want this edge, so you can say that okay, now this is not rectangular. So but you start with the rectangular, and then at the end you can make the other changes to have the orthogonal shapes. But yeah, the problem which we are talking about that is that we are considering the rooms rectangular, but the floor plans are not rectangular. Any other questions till now? Now still the problem is not very, very complicated. If you want to make it more complicated, then you can add some more constraints. For example, you can include the exterior. Till now I have drawn something, the graph like this, but then you can say that I want these 2 rooms connected to north, I want this one in east, I want this one in west, and I want these 3 in south. So you can increase more constraint, and after increasing this constraint the problem gets more complicated, and to look for a floor plan which satisfy these constraints. One more constraint which you can add architecturally is negative adjacency. Here we are giving the requirements in terms of the adjacency, but I can give somewhere the negative weights, suppose here. So I say that I want a floor plan with other adjacency, but B should not be connected to C. So you can introduce the negative adjacency, or you can add the weights like 10 and 9. So you say that this is my first priority, that A and D should be connected, so I'm putting more weight on that. C and D, if they are connected, well and good, not then well and good, but this is like the priorities. So you can make it more complicated, and you can discover many other ways to consider the architectural inputs. So by considering the different ways, you can have many more architectural inputs, and then you can propose the more precise solution which satisfy more or less the architectural constraints. One more thing which you can propose is non-planar graphs. So if we talk about the planar graphs, they are considered, or we can look them for a single story houses. But if there is a multi-story building, then you can talk of the non-planar graph. So you have to pick the planar graph, draw the first floor, then you need to look for an edge, kind of stairs which is going to the second floor, and then you can draw the second floor and something like this. So it's very, very complicated, but yes, this is one more constraint which we can introduce in this kind of the problem. Any other suggestions we can discuss after the presentation? So now what I have talked about is that we have given a graph, and the idea is to generate or to construct a floor plan corresponding to that graph. So in the literature, a lot of work has been done only in case of the rectangles, which means that if you have given a graph and does there exist a rectangular floor plan corresponding to it, and if yes, then there exists some algorithm to construct the rectangular floor plan, but there doesn't exist other kind of the work which talks about the orthogonal floor plans or the other shape floor plans. But in this particular case, so that's why we call it rectangular dual or rectangular dual graphs. So you can see here that we have given an adjacency graph with 5 vertices. Corresponding to this adjacency graph, we look for a rectangular floor plan. Now for this rectangular floor plan, one is that we can draw a graph corresponding to it, which is most of the cases similar to the given adjacency graph. We call it weak dual graph. And the other thing what we can do is that we can draw a graph corresponding to it while considering the exterior. So here we have considered the exterior, north, south, east, west, and if you consider the exterior, you can construct a graph which we call it a dual graph. The interesting property of this dual graph is that you can again construct the floor plan from this dual graph, which you can see that is in red. So you construct a floor plan, you construct a dual graph corresponding to the floor plan, then you represent each of the region with vertices. Suppose this region I put a vertex, then this is the region, means the closed boundary, and these two regions have an edge in common, so I connect them. So if I do that, then I can again generate the required floor plan from the dual graph. So adjacency graph, floor plan, dual graph, and from dual graph I can again go back to the rectangular floor plan. So if you see the papers in the literature, there is a lot of work corresponding to this problem where you are just looking for the rectangular floor plan. For other shapes and for other, the many problems are still open. So if you want to start reading some work related to this work, especially the rectangular floor plan, I suggest this is the paper, enumerating architectural arrangements by generating their underlying graphs. So in this, if you see at this paper, so they have considered this kind of the problem. Like for example, we have given this graph and the problem is to construct automatically a floor plan corresponding to this graph. So they have considered a dual graph and then they propose some algorithms, some techniques, and using that techniques you can have the floor plan corresponding to it. And if you read this paper, then through this paper you can find many more work which is related to this problem. So this problem of generating a floor plan or a rectangular floor plan corresponding to the given graph is called a rectangle dualization problem. So for this problem, it has applications in electrical engineering also. So a lot of work has been done. So there already exists some necessary and sufficient conditions, mathematical conditions for the existence of rectangular floor plans. So using that conditions, you can say that for this graph a floor plan exists, or for this graph it doesn't. There also exists some algorithm corresponding to this problem. But the interesting thing which you can note about this is that the rectangle dual is not unique. So the topological arrangement of the rooms is not unique. If you consider the graph on the left hand side, this is one graph, but you can see that there are two floor plans. Both are corresponding to this graph, and they both satisfy the adjacency requirements set up by the given graph. So again, this is a problem that if you have given a graph, how many floor plan exist corresponding to that graph, and then which one is optimal or which one is better, and then you can go into the deep. So these are the works which are corresponding to the rectangle dual graphs. One more interesting graph is outer planar graphs. So if you look for a planar drawing of any graph, let's consider the graph which I have drawn there. So if you look for the planar drawing of any graph, then it is always divided into the regions. So we call them regions. So that one region is this, the other region is this, the third region is this, and then there is an exterior region. So you can always divide the graph into the planar graph into the regions. Now if all the vertices of the graph belongs to the exterior region, like here the vertices are v1, v2, v3, v4, v5. So all 5 vertices belongs to the exterior region, then we call it an outer planar graph. This graph is very interesting in architectural design because it guarantee the existence of windows to each of the room, because each of the vertex is connected to the exterior. It means that if you draw a floor plan corresponding to it, then each of the room will have the windows. So for example this, and if you construct a floor plan, so you can see that all the rooms are connected to the exterior, and therefore all of them has a window. So if you introduce this constraint that I want a house or the floor plan, sorry, openings, yes, yeah, I am saying windows because related to this outer planar graph, this is a paper which called Windows and Floor Plans. So there they talk about this concept, outer planar graphs. So this is the one more interesting paper related to the same graph theoretical concept is the generation of floor plans with circulation spaces. So in this they proposed an algorithm where you can draw a floor plan with spanning circulation spaces, so that the circulation space is connected to each of the room and they are connected to each other. So this also totally depend on this graph theoretical concept. So now the connectivity of the floor plan. Suppose we have 2 floor plans, then on what basis we can say that one is more connected, one is less connected? So we need to define some criteria, and there exist many ways to compare. So one way to compare the 2 floor plan or the connectivity of 2 floor plan is by comparing the number of edges in their adjacency graph. Suppose here we have the 2 floor plans. So you draw the graph corresponding to both the floor plans, then you count the number of edges. So here it's 15, here it's 11. So you say that this one is more connected than this one. So if we talk about the rectangular floor plans only, then a rectangular floor plan or the adjacency graph of a rectangular floor plan can have at most 3n minus 7 edges, where n is the number of the rooms. So which means that we can say that a floor plan, a rectangular floor plan is best connected if its adjacency graph has 3n-7 edges. So recently I am working on the concept of the generic rectangular floor plan. So the idea, because the problem is that you have a graph and you need to construct a rectangular floor plan corresponding to it. So you always need to check the existence of the rectangular floor plan and then you have to construct it. So what I am thinking is that I can propose a rectangular floor plan and it guarantees that it always going to satisfy the constraint provided by the user. So if we manage to do that, then we don't have to check every time and we can say that use this rectangular floor plan which is generic. It guarantee that it satisfy the constraint, whatever constraint you gives, and if it is not satisfying the constraint, it means that there doesn't exist a rectangular floor plan corresponding to it. So the work is in process and very soon I have the result, so I will share the paper with you. So coffee break because I think till now it's very hectic or mathematical presentation maybe. And if any question, because now I am going to talk more precisely about my work, what I have done till far. And this was the journal presentation. So if you have some questions related to the journal presentation, please ask. Otherwise, you move forward. Or if you want to take coffee, go ahead. Yes. Oh, okay.
Did you consider as an evaluation, because you've been considering for architectural floor plans, simple and directed connected planar graphs. But for instance, in the case of an airport or a very complex floor plan where we have specific ways of communication, for instance, exit fire exit doesn't need to be very complex, but fire escape exits. You can only go in one way.
Yeah.
So is it possible to integrate this analysis directed graphs?
Yeah, that's what I'm saying, that's the beauty of the graph. You can add so many constraints like this for the particular purpose. Like I talked only about the house or the buildings where we don't need the directed graphs or where we don't need the weighted graphs. But we can introduce, that's why there are so many different kind of the graphs and you can use some properties to design. So for the particular purpose, yes, you can use the particular graphs. In mathematics, what we normally do is that the idea is to give a general theory so that anyone can use it. You know, if you have the general theory that, okay, this is the condition or this is already a inbuilt software which you can put the input and it can say that, like for the planar graphs, there are some already existing algorithms. If you draw the graph and you click the button, it will say that it is planar or not, because they have developed the general theory. Now you draw the graph and you can check. So yeah, my work is more concerned with developing the general theory.
What kind of, till now, what kind of problem has each edge? What kind of architectural quality has each edge on those graphs?
Architecture.
It's a door, it's a wall, it's a window, it's a...
Yeah, normally if we say that the two rooms are adjacent, it means that there is a wall between them. Because if there is a wall between them, you can always insert a door between them. Yes.
Okay.
Yes.
It can be adjacent but don't have a door. You don't.
Yes, this will leave, yeah, I think this will leave to the architects. Once we have a compositional schema, then you know architects can always modify it, they can see it and okay, let's remove this door, we don't need it, let's put it here, something like this. So this is like the last stage thing which architects can do. But initially the main thing is to check the feasibility, that there exists something like this or not. You can say that, okay, I want this room to be connected to all 10 rooms, and then I can say that there doesn't exist any floor plan for this constraint. So remove something, or otherwise there won't be any solution. And if you do this through computer, then it increases the usability. Anyone can check it, anyone can use it. So if you develop a theory, and from theory there comes the algorithm, and from algorithm there comes the users.
Just for spoiling the thing, the main goal is to get optimum solutions in terms of connectivity.
The main goal is to satisfy the user's requirement. You asked me that I need these connections, which we call adjacency.
And I give you the graph.
You give me the graph, or you can directly say that this I need this connection, so I can draw the graph for it, and I need to propose a floor plan satisfying this connection. So one thing that happened, that if there is some theory, I can say that no, there doesn't exist any floor plan, because what you are asking is too much. So just remove something, or I can propose just remove these 2-3 things, then it is possible. Then you can ask that no, I don't want the rectangular floor plan, but let's say the other shape. So then again there comes the problem that okay, this shape is possible, but this is not possible. So these kind of the things.
And what happens if I give you an under constraint graph? So I think, oh, I need this and that, but the rest
There is nothing like under constraint graph. Yeah, I can say that there exists a solution for it, or there doesn't exist a solution for it. So there are only two cases. Why there doesn't exist? Because over constraint. It cannot be under constraint.
Now, what I was thinking is in terms of an architect or a client saying, oh, so I want a big room, a big living room with a kitchen, but then I want the rooms to be far away, without specifying everything, you know.
Yeah, then maybe the graph is disconnected or something like this, but it doesn't have some properties.
We introduce the connections that you think that might be possible. In that case, maybe you need to create the constraints in order to make it feasible.
Yeah, but that
the idea is to develop this prototype, because it's like everyone cannot reach to the architect, but if there is this very simple kind of the prototype where he knows that okay, let's give this 10 rooms, I want 10 rooms and I want these connections, so he can enter the connections, and then there are some floor plans.
To build 10 rooms, he has money to pay a night.
No, but like in India, I think 80 to 85% people don't go to the architects, and the population is 1.2 billion. So you can say that 1 billion people don't consult the architects.
And you're helping them.
I'm not helping them, but I am giving you the problem.
Should this audience know something about topology?
This audience?
This audience, yes.
I don't know.
They should know something about that, isn't it?
No, not that much. I think not that much.
But it's always a plus.
Yes, it's always a plus to understand the solution because here I am not talking that how to construct the floor plans, how to develop the compositional schemas and this and this. I am just introducing you to the problem. If I talk about this construction and the compositional schema, then yes, we talk about the topology also. But I am just talking that this is one of the research topic, and there are many problems which are open in this field.
But if I understand, so the graph is somehow a way of drawing the brief for the future floor plan.
Yes.
Is that a way, but I think yes, to introduce, because it seems that now the brief is simply about connection between rooms and maybe the orientation, but to develop it through floor plan from a brief, for example, it's important to introduce regulation and normative constraints, that is to say minimal dimension for the rooms, or a connection of some rooms with light, and some rooms can also not have this connection to the light. So all those kind of information should be introduced in the graph, or are constraints that happen.
You know, the beauty of rectangle is this. It doesn't work with the sphere or with others. If you consider like these spheres, and if you try to develop some compositional schema, they have a lot of gaps and everything, a lot of problems. But with rectangles, if you have some compositional schema, then somehow you can introduce the dimensions and the other things, because the rectangles are very flexible. They only go this and they only go this. So if you go this, the other one shrinks, or if you want this or this. So if you have the compositional schema for that, which in the next part we'll see that the floor plan satisfying the dimensional constraint and some other constraint. Yes, it's a step-by-step thing. So once first you satisfy the topological, the connection thing, then the dimensional constraints, and then one by one, like the window and this thing and this thing. So that's what I'm saying. What I'm talking about is very journal work, which is like for to reach to the larger audience. If you want the very particular thing, obviously there are so many architects and you can help them.
How would you compare two graphs? What are the common criteria?
In what sense?
For example, no, when I imagine two spaces that you draw graphs out of them, I would compare them visually.
No, to compare them, the first thing which you need is that they should have the same number of the vertices, like the floor plan. Sorry?
To be comparable.
To be comparable. And then there are many problems. Like one more problem is this: if there is one graph and then you look for the distance between each pair of the vertices, like v1 and v4, the distance is 2. Then here the distance is 1, and you draw one more graph, and you can find the sum of the minimum distance, because architecturally it's very interesting, the sum of the minimum distances. So this is one thing. So it depends like what you are looking for, and then on that basis you can compare them.
Is there any way that links graphs theory with like spatial experience or something of value? For example, that graphs that are better connected provide, I don't know, better social activity. I mean, have you just have read something?
I didn't read, but there must be something like this, because this is the field which even the mathematicians are exploring so much. Like it has applications in electrical engineering, in other engineering fields, and every day, because this is how the graph theory evolved. It just for a few seconds, it start with the 7 bridge problem. There was a village and there was 7 bridges in the village, and someone asked that, is it possible that I pass through each of the bridge without repeating anyone? And people start thinking about it, that is it possible, is it not? They started going this and this and this, and they didn't find the solution, something like this. And then there was a mathematician, Euler, EULER, and he drew this bridges like a graph, and through graph on pen and paper he started connecting the things, and he said, if you follow this route, then obviously you can pass all the bridge without repeating it. And then comes the concept of the graph theory. So it already came with a lot of applications. It is very applied field in mathematics, and you can find applications everywhere. Which graph?
Planar ones.
Yeah.
Because it means that you make a circle.
Planar graphs, if you draw the graph of any floor plan, it is always planar.
Oh.
There should not be any edge crossing. So that's why if graph is non-planar, it means that there doesn't exist a floor plan corresponding to it. This is very simple theory. So if you need a planar graph, or if you consider the constraint, it should be planar, otherwise there is no floor plan. Should we move to the next part? So one of the related problem, well-known problems, is space allocation problem, which is computationally arrangement of room inside a polygon. So you have given some rooms, different rooms of different sizes in particular rectangle, and then you have given a polygon, maybe something like this, which is made up of a straight line. And then you have to fit them inside this polygon. So first thing is that, is it possible to fit them or not? If it is possible to fit them, then you should have the minimum waste space or the voids or the gaps and this kind of the problem. So they call it a space allocation problem. Now if you want to relate it with architecture, so there is a kind of the matrix which was introduced. I saw it in a book by Khaled, which is Architecture's New Media. There is a chapter space allocation. So there he introduced this weighted matrix. Now let's talk about the complex building. Till now we are mainly concerned with the houses, but if you see the complex building like hospitals, like universities and this kind of the things, it is very difficult to give the adjacency relation by graphs. You cannot say that easily that okay, I want library here and then library should be close to this classroom and this and this. So what he said that you take an existing model like an hospital and then you compare the number of trips between the different rooms. Like you have the room of the nurse, then you have the room of the patient and you have the room of the doctor. So you see that how many times the nurse go to the room of the patient, maybe 25 times in a week, or you can count per day, and you can see the number of times he is going to the room of the doctor or particular doctor, so maybe 15 times. So it means that the distance between the room of the nurse and patient should be close than the distance between the room of the nurse and the doctor. So on this basis he introduced this kind of the weighted matrix where they count the number of trips between the different pair of the rooms. So like here there are 16 rooms and then you normalize them on the scale of 10, so which means that 10 is the maximum number and 0 is the minimum. It means you are not going to that room or you are going 2 times, or maximum you are going to the 10 times. So this is kind of the matrix which they construct from an existing model, and then they say that using this matrix now you need to construct a floor plan which optimally satisfy this matrix. So which means that the problem is to find a floor plan where the sum of the weighted distances between the room is minimum, because if distance is minimum it means you can go there more often and don't have to walk that much and they are more adjacent. Or in other terms, you have to maximize the connectivity of the floor plan, which means that you need to have a floor plan which has the maximum connectivity. So let's say that we have given the design briefs where we have given the topological constraints by the matrix which we have already seen. Then there are 15 rooms. BR1, BR2 are bedrooms. Then there are 2 guest rooms, 2 bathrooms, 2 WC, a living room, a dining room, a kitchen, 2 studies, a library and a playing room. And we have their width and height. So each one is, first one is width and the other one is height, and they are the rectangles. And then we have given the shape of the floor plan. So the problem is to fit all these rooms which are rectangular into this shape while satisfying the topological constraints which are given in terms of the number of the trips.
Both numbers mean?
Width and height. So we have the dimensional constraint, we have the topological constraint in terms of the number of the trips, and then we have given shape. And this should be, since it's space allocation problem, so it should be done computationally, like through an algorithm that you take this input and then it fit it into the plus shape floor plan. So now if you see this floor plan, and since we are dealing with a complex problem where the number of rooms can be very big, so what we think that we can divide it into the rectangles, and the maximum number of the rectangles, because we can divide it into the 3 rectangles also, something like this. But since the number of rooms would be big, so it's good enough to divide them into the rectangles. So we divided them into the 5 rectangles, which means that we can divide the given rooms into 5 groups. Then for each group, we construct a rectangular floor plan, and then we adjoin the 5 rectangular floor plan to have the plus shape floor plan. Now we have given the topological constraint. So on the basis of the topological constraint, that means on the basis of the number of the trips, we divided the given rooms into 5 groups. And you can see that somehow on that matrix, because it's kind of real matrix, the group formed are very interesting. So first group has 2 guest room, 1 bathroom and 1 WC. The second has living room, dining room and kitchen. So it means that they should be together. The third group is 2 offices and library. The fourth group WC and bathroom. And the fifth group has 2 bedroom and playing room. Now, for each group, we construct a rectangular floor plan. Now, earlier we have seen that normally we have given an adjacency graph, and for that we construct a rectangular floor plan. But in this case, we don't have any adjacency graph. So what we think is that let's consider the best connected floor plans, because best connected floor plans have the maximum connectivity. That means the floor plans with 3n-7 edges. So corresponding to each group, we construct a best connected floor plan, and since the dimensions are not in our hand, so there is no guarantee that they will fit in the shape of the rectangle. So we introduce these kind of the extra spaces so that the shape will remain rectangle, and then we adjoin these 5 rectangles to have the plus shape floor plan, which has some extra spaces, and at the same time it automatically generates the graph of this floor plan. So like here it has dining room, kitchen and living room. There are 2 bedrooms, playing room, 2 offices, library, and this is now done computationally. So to do this, I developed a prototype where you can give the inputs. N is the number of the rooms, so you are looking for 15 rooms. Then there are the name of the rooms or their functions. Then you can give this weighted matrix which gives the number of the trips, and then at the end you can give the width and height. So you take this input, and if you run this prototype, I hope it's working. So it generates a graphic user interface where it says that okay, you have the 15 rooms, then there are the 5 groups. So name of the group: group 1, group 2, group 3, group 4 and group 5. Now since we are dividing them into the groups on the basis of the number of the trips, and we are using an algorithm for it. So algorithm don't understand, you know, the feelings of an architect. So you can say that no, I am not happy with this room particular, I want to change this room from one group to the other. So this can be done from here. So you can change here. I am not changing it, but you can change here. Then if you see the plus shape floor plan, so there are 5 positions: center, then left, then above, then right, and then below. So each group can have any of the position. So that's why you can choose the position for each of the group where you want, maybe somewhere in the left or somewhere in there. So there it can be choose from here. And then for the best connected floor plan, you can have 8 different compositional schemas. So this all compositional schema generates the best connected rectangular floor plan. So you can choose any one of the compositional schema which you see, like if there are 5 rooms, then you can say that, okay, I want that compositional schema where 5th room heads towards north or something like this. So you can choose this compositional schema from this GUI. There are eight possibilities. And if you do this all hard work, then you have the plus shape floor plan and its graph. So we have just worked with the plus shape floor plan, but still the problem is open for the rectilinear floor plans, so that we can consider all the orthogonal floor plans, and then according to your desire we can say that, okay, if you want L shape, then here is the L shape floor plan or the other shape floor plans. Or the problem is to look for the best shape which fits the given rooms and the adjacency requirement. Thank you very much. Any questions? Oh.
You said that the input was number of rooms?
One of the input.
Number of trips and the area of the.
Yes, area of the rooms.
So we have 3 types of inputs.
Yes, this is what I am considering. Then we can add inputs. This is the start. We can always keep adding the other inputs.
At a certain point, we had some conversation about certain principles that architects like to follow in design. Like I gave you the example of John Habakken, where he gives those ideas of planning thematic bands which are occupied with certain kinds of rooms. And that strategy actually generates a kind of an order in the plan, while keeping positions where you can connect the rooms in a, let's say, consistent way. Could you adapt this strategy to this more, let's say, generic structure in a way that we could also consider this kind of composition constraints, let's say?
Yes, I think.
Because I think that would be a great step towards something that.
Okay, if you have that paper, okay.
Really think, wow, this is really generating something very useful.
Okay, so if you have that paper, send me, and okay, we can discuss over it.
Okay.
I think there's one thing lacking in this tool, which is you always talk about living spaces, living rooms that are intentioned for a particular function.
Yes.
So, and you don't talk about transit spaces.
Circulation spaces.
Yes.
Yeah, this is I am working over it.
It would be relatively easy to include this
yes.
in this theory.
Yes.
Because, circulation space is a space that must be connected with several rooms at all.
Yes.
And perhaps it has to have some constraints in area or in dimensions, width, height, dimensions.
Yes.
I think this would envision.
Yeah, this is, I'm about to add, Yes. Yes. Yeah, I'm working over it. I'm about to add kind of circulation space which is connected to most of the rooms, so that you can see the path that, okay, from here you can go like this. So yes, I am adding this.
With the emblematic and less architecture in that sense.
Yes, yeah, I will add it.
I think you should distinguish between windows and doors, because it's
yes.
idea to understand the relation.
Yes, we can add some kind of.
Of course, this circulation space is one more thought with some kind of.
you showed the, I think not the last one before, but this one in this shape.
Yeah.
So somehow, what's happening is that the circulation spaces are really what remains of the other spaces, or so. For example, in this, the white rectangles.
Yes.
Is the remaining space.
Yes.
From the module,
yes,
say, and then the dark gray are the remaining space
yes,
from higher
yes,
levels. I'm not sure if these could be the circulation spaces because of the dimensions of them. For example,
yes,
in this case, you have very slim parts. So
yes. Yes. So one idea what we are thinking of is that initially we propose the rectangular rooms, but somehow we can convert into some kind of the orthogonal rooms so that there won't be any extra space. The other idea is to connect these extra space in a way that they all should be connected. So yeah. So
because I imagine this is like a first iteration of.
Yes, it's the very first. Yes.
Eventually, yes, those remaining spaces could be used for circulation, but
yes,
maybe it needs some more rule, maybe one or another. Because
no, that's what I discussed with Professor Duarte also, that what exactly we can do just after that. Still, I am waiting for his input, that because this is the initial stage which is taking some input for a very general user, but now let's add some architectural stuff to it, and I think that is the reason I came here.
Yes, it would be also nice to rate how much do rooms overlap.
Yes, yes. So yeah, one way to avoid this extra space is to consider some overlapping, something like this.
So you may have you may want to have living room that is completely overlapped with the dining room, and then you want room just with small adjacent spaces enough to have a door there.
Yeah.
Nice constraint. The thing that you're very like doing this year, developed once, isn't it?
Yeah.
It's very nice.
Yeah, but this is the problem. Like sometimes I get stuck because I need architectural inputs. It's what I am doing is kind of computational, but if you don't add the architectural meaning, then at some point it is kind of maybe no use, or it gets stuck somewhere. So that's what I'm looking for.
There are basically two things that architects use every time they design a plan for any kind of building, maybe a house, maybe another type of building. But there are always two types of grids that we use. One is compositional grid, and the other is a structural grid. So all the other requirements somehow fit this concept. We can talk about things that don't fit into this kind of logic, but this is, let's say, common logic. So this would mean, considering the generation of the rectangular aggregations based on some matrix that is imposed to this generation. That would mean that you should have, let's say, this the definition of this matrix somehow, and then the generation of the rectangular composition on top of that. There is also something which is, let's say, generic design process that architects use when they have this matrix and put rectangles on top of the matrix. Sometimes, like what it happens here, for instance, to the upper rectangle where you have the ER space, which leaves a lot of white space,
yes,
or leftover space there. The architect might consider the possibility of using a different proportion because it leaves a lot of space.
yes,
So having also space in terms of generation to adapt these proportions could also be an interesting tool. But of course, these are, let's say, kind of fine-tuning details that maybe could just
yes,
be a kind of interactive
yes,
interface that
yes,
can be built somehow in this kind of system. And again, another thing is the problems. I mean, an architectural design problem is a sum of many different kinds of problems, and the solution is typically a compromise between all of them. And it is holistic in the sense that it's not a direct sum of the solutions. Okay, so let's say that the way the partial solutions are organized together is also a design problem.
yes,
okay? And that means, I would say that this kind of organization problems, because this is essentially one part of the design problem,
yes,
which is the spatial organization
yes,
of the program, is usually not the most difficult part of the project to solve, except in cases of very large programs and very complex programs with a lot of constraints, like, let's say, a hospital,
yes,
an airport, things like this,
yes,
which we can imagine immediately that the large program generates a lot of difficulties. In that sense, I would say that I see a lot more application of this kind of approach in very large programs than actually in small programs. Although the tool can be very useful anyway. But to make it more useful for, let's say, smaller projects, with it has to have a lot of interactivity with the other topics that architects use. So I would say that these other layers, like the structural matrix, the compositional matrix, should be things to be considered.
yes.
Well, I think this is designs of thought that is kind of that used to do the aesthetic things and the complicated guys. But of course, hospitals is a big example to start with. But I can we have an idea. Start with the operating room. Operating rooms in hospitals are extremely difficult to solve. There are many people with their ideas. They know all the things should function, but at the end we want to really know what's the best solution. So I think with this kind of tool, without aesthetic of things, because just want to work with the functions, and I think it's a good start to test the tool with a simple thing, with a very small simple thing, to see if it works. Because operating room is a kind of difficult thing. Okay? There's different circulatory ways to put the patients, the doctors, the things, I don't know the name, but everything should work with this big room. But it's not easy to do that. It's a really simple, difficult thing when you design it operating room. At the end, we are not satisfied.
Okay.
There is something that we think someone or another time we should be better than we did. So this tool, I think it's a kind of thing, good strengths to play with.
Yes, to play with, you have to start, yes.
If you want, I can give you some ideas of fraction in the operating room.
The reason why I'm talking about making things big is that is too much. So big too much. Yeah, of course. I mean,
It's over, no?
Program, but I'm thinking about it in terms of what is a constant process in architecture. There's always some kind of larger scheme that defines the composition. Okay, yeah, and that is usually something that guides the other parts. And I think there are some ways of approaching that. Once I developed, it was made in Grasshopper, although it was a depression code. I developed a code to define an urban grid based on that famous rule, subdividing rectangles and putting a street in the middle. Okay. Basically, what happened was, and I will simplify. I had a large rectangle, a large urban area. It would design the first street, second street, fourth street, so on, like this. And the code would stop when it would reach rectangles with a certain area. So below a certain area, it would be done. But we could have problems like that. Yeah. But we could have problems like having, for instance, very small and long rectangles, which might be nice for. Sorry. Oh. Okay. Which might be nice for. Okay. Might be nice for. Simply for a pictorial composition, but to define urban blocks, it doesn't make sense. At a certain point, we found out that the best way of solving this would be to define a matrix to orthogonal matrix to fit all the subdivisions. So basically, we had to define, let's say, the grain of this, and we would make these streets fit that grain. That meant two things that were meaningful in terms of an urban grid. First, we could have coincident streets, which means we could have some crossings, street crossings, really orthogonal in the right place. That could introduce some meaning into the final design, and we could also constrain the design in such a way that we could define a minimum of a certain number of modules to define the subdivision. And in the end, we would have the right proportion. And and we created a parameter that we could change, which was the size of the grain. And if we would change the size of the grain to a higher value, the number of streets that were being generated in a coincident way would be more than if the size of the grain would be smaller. Okay, so and was just by using this extra parameter, like the size of the grain. So it's a way of generating rectangular organizations with making it fit into something that makes sense, leaving some issues of proportion reasonably open, but still giving preferences, let's say, regarding some kind of possible organization. But it means that you need to define some basic matrix below the whole thing. So this is simply let's say a suggestion, in the sense that in the end you can generate meaningful arrangements of rectangles, but still keep something, some bigger structure and a way of organizing this bigger structure. So it's basically working with two layers. One is one layer of constraints where you may have one or two variables, and the other is defined by the graphs and the adjacency matrix. So this is just a suggestion. We can discuss it later a little bit more.
There's something I wanted to add. As far as I understood, in your model, you try to look only at the overall connectivity. Yes. What is the? I mean, I think that from an architectural point of view, probably it will be more interesting to look at the specific connectivity from one room to the others. Are you taking that into account? Am I missing it or not?
Like in this particular case, we are taking it into account on the basis of number of trips. Because
number of trips. So
yes.
So there is a kind of evidence that the number of trips translate into into connectivity.
Yes.
Okay.
Could you introduce kind of margin to the area? For example, 5% or something when you have this kind of white spaces, so they can adjust if needed.
Yeah. So yeah, that's what I am working over it. That how to optimize these white spaces. So like we can give some mathematical theory that if you use this algorithm, then the white spaces would be minimum. Yeah. So here I haven't added it, but yeah.
Because that's what we're always saying, to make a structure or a composition line.
Yeah.
You can try to adjust to some underlying geometry, or I don't know. For example, in modernism they use 60 centimeters as a module, but if we have some other type of module, then it's then it is easier. Also, it's optimized construction costs, because it makes things modular, and it can align structure.
Yeah.
Also, another thing that maybe you could use sometimes the help of an architect, but still I think you can do it yourself. Sometimes looking at what has been generated, just look at it and think, what could I do better than the algorithm? Okay? And when you look at that result, you immediately see a few things that could improve. Okay? Let's say that you mirror this result, okay? So that you have this space related to this empty space, with that empty space, and we can see that we start aggregating all the empty spaces in a way that probably we are having we are using too much space to solve the whole problem. So first, I just mirror this thing, okay? Then let's imagine that all this is mirrored the other way, so that this connects this way, okay? And again, we have connections between all these things, and we start seeing that things can have, you can have a circulation inside, and still you have too much space in that circulation, okay? And things can start to improve, and we can see how they could really compact a little bit, because if we have this space here and this space here, we immediately see that things can be really be more compressed. So the question that comes later is, okay, we can see, do this with just with a simple reasoning about the problem. What went wrong with the algorithm? How can I improve it? Okay, so what is the problem? Sometimes it's just a question of having some algorithms that test a few solutions and try to through some process test several solutions and improve it. Could be a genetic algorithm or something like that. It picks up one or two solutions because they fit the matrix, but then they're using some other procedures that can improve the solution. But okay, just a few topics that I think that at a certain point need to be addressed.
Yes.
I think you can still improve this using the approach that you're having until now. It can be improved, but at a certain point, it's always important to look at these things and see what is going wrong. There might be some wrong assumptions. Okay.
Yeah.
And sometimes we need to get back, is the result occurring systematically? These things that we point out as not exactly what we wanted, the result of a bad algorithm or a bad assumption. Okay? Could be both. So it needs to be, let's say, questioned.
Yes.
I have a question about this graph here, and I think I didn't become totally elucidated about the workflow you propose. So you have initially you have to ID several rooms or spaces and the connectivity constraints.
Yes.
Okay. And then that gives birth to a graph.
Yes, in the algorithm, yes.
Okay, but you said that this kind of arrangement of spaces rooms should give birth to a graph with no crossing edges, a planar graph.
Yes, yes.
And how does this graph, because this graph here should have a planar form, not
but this should
be interlaced. No?
Yeah, this should be planar, because
why
we can.
Why does it appear like that?
Yeah, because I haven't drawn it, because we are doing through computer. So what I am doing is that I am giving this. I have added a code that two rooms are adjacent. Then draw these two rooms or name them two and draw an edge between them. So while drawing them, it's because it is done through computer, so it is not considering that it has to draw it in a planar form.
These graphs are useful is to schematize
Systemize.
To show in a graphic manner the articulation of the spaces.
Yeah.
So in this form, I think it doesn't serve that.
Yes, but
there are some system connected to this. Could you do me this? The slide.
Which slide?
Let's see. For instance, WC1 is connected to BA2.
WC1 is connected to BA2. Yes.
And GR2. The connection to GR2 is through an extra space.
Yes.
Okay.
Yes.
For instance, you have the kitchen.
Yes. So kitchen is connected.
Should we also connect them to
No, it's
It is the same criteria. You have this connection here. It looks into GR2.
yeah.
Okay. So if this connection is through an extra space, you should maybe have a connection here. They
Yeah.
are not adjacent, but
Yes. It's like, since we have to, because this part is done as a, not as an architectural thesis but as a mathematical thesis. So what we did is that we have to define adjacency in a very mathematical way. So the way we have defined adjacency, there are some particular definitions. Yes. So through those definitions only, these are, I'm not telling you the definitions what we have used, but we have introduced the definitions in a very general perspective, because this is how mathematics, I think that's the problem. When I defended my thesis, I have to defend it on a very abstract level. So that's why it's very mathematical. So it was very hard to convince people from mathematics about this thesis. But since I get involved that much there, so when I came to architects, they were very specific. So they are looking for a very specific thing, and it's exactly opposite of what like I used to work or I used to think. So okay. Yeah, and about the
how it can be theoretically useful in the work used to do.
and about this like reading of the graphs, so we consider a lot of inputs. We like, if you see that graph and if you have to see the shortest path, so it's like you can see all pair of shortest path here. So if you have to see like between BR1 and GR1, so you should go to PR, then BA2, then BA1, then GR2, and then GR1. And these are the distances between the each pair of the rooms. So this is also done computationally through the graph. So we can read the graphs, and because through this prototype we can generate 4 million different solutions. And if you see, because in mathematics that matters, and now the next question comes that how you compare two solutions. So then again we introduce some mathematical theory to compare them. So like the sum of the weighted distance. So we calculate the distance, and we can say that okay, if we consider this floor plan, it has sum of the weighted distance minimum, or this has the minimum area, or this has the this thing. So on the basis of these mathematical covariants, then we compare the different solution. So this prototype also computes a lot of these graph properties. For no, you have, that's why I show you that graphic user interface. So you can keep changing the input and it keep presenting the different solutions. So by keep changing the input, you can have 4 million different solutions for one input.
You know, one of the typical ways of reasoning in architecture is not finding out all the possible combinations and then choose one. It's usually setting out first all the constraints that the problem has. So it's shortening as much as possible the design space, because the design space is really huge.
Yeah.
And the way architects used to do traditionally was essentially, first of all, based on experience. So you would put immediately a lot of solutions on the side and
yes.
start working on particular possibilities. And when we do it in a computational way, the tendency is always to check all the possible combinations and then clean it. And I think there's a lot of waste in this process.
Yes.
So probably, and this brings again to the question of assumptions, because we need to define a lot of assumptions, means that we should have some way of constraining things at the beginning in a very hard form. the biggest problem in this, from the computational point of view, is that architects will say, well, the main constraints are this. And then you start getting results, and in the end they will say, no, the main constraints are not, these are other constraints. So it means that there must be some way of, getting results and coming back. This feedback loop is particularly important. Usually, in a computation implementation, people tend to forget these loops because they are difficult to implement. If we really want to have useful tools, at least in design, any kind of design, we should keep feedback loops somewhere in the process and as interactive as possible. One of the difficulties is to understand where we should have those loops, okay, and how the loops should be implemented. Probably, and I have to say that the presentation that you made is very clear. It's very easy to follow all the steps and all the degrees of complexity. That is very, very good. And I think that you developed a lot since the first presentation that you did, so that's also very good. But there is a point where you need to consider all these steps. Probably there is still one step in complexity, one ahead, where you can improve a few of the things related with the last things that I told you. But there must be a moment where you consider this this topic of defining where the feedback loop should be, how to define that feedback loop, and probably relate that with those layers that you should have underneath the rectangular arrangement generation.
And I agree with you. Designers have one of these is authority. I said this is a good solution. And of course they have no time, so they have to stop at some time. But I think you have some studied heuristic methods.
Heuristic method, yes.
There are some ways to go back and forth.
Yes.
To try to go quickly to the best. The best for at least to go study that and you can
No, like even when we did this work, and there was only because this was the problem we worked, and then there is one solution. And like in the last year of my thesis, we thought to develop this computer model, which is, at the very initial stage. And when we developed this computer model, then we found very interesting thing, because sometimes it happens that since it is giving so many solutions, that's okay. But still sometimes it happens that we cannot imagine everything. For example, it has 4 million solution. In this case, it has extra space here and WC2 here. But if you see the next solution, maybe WC2 would be here, or this extra space would go somewhere. So it's like, we find it very interesting because we cannot visualize everything. And that's what computer can do. When you write a code and it's something which you didn't expect and it comes out. So maybe it is not very useful, but it is interesting, and that's what mathematics do. We look for interesting things. No one knows that the mathematics has application or not. Someone found application, something like, but it should be very interesting. Something new should keep coming and something like this. So that's why initially we developed this computer model. But then I thought that yes, it can be really useful for architects. So let's move to architecture department and let's do something which is more relevant. But initially it was not the idea to do something which should be, the idea is to do it in a more general way, which you can find applications in other field also. It should not restrict to architect. But then I found my interest and it is going like this.
Because I think we start thinking the habits. I think that everyone just experience that is repeating the same kind of house or same kind of, I don't know if we have it from our childhood memories, something like we have some, and that breaks all those kind of habits.
Yeah.
Yeah, because we would never think that way.
You know, in architectural creativity, and I will extend this to art in general. Certain approaches to creativity in the modernist era, because contemporary things tend to be a little bit more complex. But at least, so I would say until the 70s, the approach to art would be to find a personal style, personal language. And it was let's say, a very individualistic approach to art in any artistic field. I will find my own way of expression, and that makes the need of the artist to create a very strong will about the things that he or she wants to explore. And sometimes might be a system of composition. So other times might be the use of a color. Other times might be a use of a matter. And in architecture, it could be a material, a structural approach, kind of a spatial approach, and it changes from architect to architect. And if you look at that with a lot of attention, you will see that there are very extreme cases of exploring these approaches. These were, for instance, an extreme example of working with partitions which are basically rectangular walls that don't touch each other. They simply, subdivide spaces and leave some spaces between each other that allow for things to pass. So it's a different kind of approach. It's very personal, and there are other examples. But it's always this, okay? So it means that at least in modernism, the best artists, architectural or any other kind of art, are people who define a lot of constraints to begin with. I'm just going to explore this. There's no other things to see. My field of exploration is very tight and very precise. And the fact that they define that is part of the generation of their own style, of their own quality. Of course, there are functional issues and other things that we need to solve in the case of architecture, but still, they don't consider anything that is outside that space.
Yeah.
So the computational approach starts by, simply ignoring this. So my question is, would there be a way of developing tools that allow to have really intelligent functions for design exploration, especially when we have very complex problems to solve, but still allow the designer to have this kind of will on top? Because in the end, any designer will otherwise they will ignore the tool because it doesn't practically do what it wants. Of course, the contemporary situation is a little bit more complex because designers tend to explore different languages every time they do a new project. And you can see that on a lot of architects. Some keep their own language in a very precise way, but others really try to explore different kinds of approaches. For example, Grand Coolers is very obvious, and also Afro and which are architects that really explore completely different approaches in every design. But yeah.
Yes.
Isha, may I just, sorry again, just one thing. Did you ever consider overlapping on the same graph, not the same graph, on the same simple graph, which means the plan, the floor plan? Did you ever consider making different graphs and evaluating different approaches, either connectivity, visibility, shorter path, preferences, and then evaluating them at the same time?
No, I haven't. But yeah, this need to be done because yeah, someone is good for something and someone is good for something. So till now my work is just concerned with this thing, but yeah, that's the one of the problem. Like some of the weighted shortest path should be minimum, and yeah, these kind of the things, optimal thing. And yeah, one more thing is this: I need to consider this overlapping also, so that there won't be any void spaces. So many ideas are floating.
Thanks again.
Thanks. Great job.
Thank you so much.
So now, for those who still have a little bit of time, Camila would like to present what she's looking into and joining the session and giving us a glimpse of her work. Do you have the adapter? Oh, can you use your laptop?
I have adapter. You know, just set it.
Yes.
Use a computer or
What? I don't need computer.
Can Camila present on your computer? Okay.
Vamos pôr.
Posso, se calhar, parar e começar?
Não, fazem um vídeo.
Okay, as all of you know, I'm a PhD student from the Politecnico di Milano, and my PhD work there is about adaptive reuse strategy for office building, converting them into residential buildings. I jumped in shape grammars just during my last year of the PhD thesis, so I'm here trying to make an application of this methodology to the work that I'm already done and that I already did before. So this presentation is divided into two parts. The first one where I will give you a brief overview on my thesis work to make you understand the main objective of my thesis. And the second part is about what I developed here during the last month. So, as some of you already know, my thesis is to investigate the advantages of intervention on built environment rather than the application of demolition strategies. And the object of my thesis are the office buildings that are abandoned and not used, and tries to explore strategies of converting them into residential, particularly investigating on the strategy of the incremental facade that I will explain you quickly later. And is addressed mainly to both public administration and public and private owners, investors in real estate field, that in order to show them and to make them understand the adaptive capacity to be reused of a building, and also to figure out some strategy and application already effective to that purpose. So the research field starts from this big gap that there is in the Milanese urban region, because all my cases are from that area. It is the gap between a really great number of offices that are completely abandoned and not rent, and together with that, a huge demand for housing at an affordable cost, because all the new housing in the region of Milan has been just for very high standard of housing demands, while there is this big gap. And the strategy, the possible strategy of converting office can be an answer to this situation. Of course, not all the buildings that are now unused office will have a conversion to housing. Just in particular cases, this can be an affordable solution. One of the main aspects for which an office cannot be refurbished as an office is, for example, the obsolescence of the building for a particular, with respect to the new way of working, so the structure of some existing building are not compliant anymore for a function that is an office function, or for example, the energetic behavior of those buildings is not compliant anymore with the standard, high standard that are required in the Milanese market for offices. And also there is a really exceeding number of office buildings with respect to the market request. There is a high vacancy rate with no perspective of short-term reabsorption of those buildings. And together with that, as we saw before, a high presence of housing demand. Yes. Yes.
Because all Italy wants to go there. Okay. I don't know why.
Yeah, that's true. The data that I was showing before is just in the province of Milan. The request, that is an old data that I need to update, but for the period between 2006 and 2015, there was a request from 90,000 to 140,000 new dwellings. And also, not only the market of the owners and the Milanese people, but there is a huge market of people that just rent apartments. So because everybody is really moving to Milan for different reasons, mainly for working. So the structure of the thesis is divided mainly into 4 parts. The first one was a data collection on all the urban regions. So I made a census to understand which were the buildings, how many buildings, in which location they were allocated, and to understand maybe possible links between the location and the structure typology, the constructive typology of the building itself. Then to make a benchmark, considering similar cases of reuse of office building into housing, and also benchmark of cases in which the main element of intervention was the facade. When I talk about facade, I'm not talking about a bidimensional surface, but I mean a surface that goes from 60 to 2.50 meters of depth that can be really useful for introducing in the building all those elements that are missing and that are necessary for an adaptation of the building. Then the third part was really focused on those elements, so on these incremental elements to be added to the building to make them work as residential building. And the last part is the application of the shape grammar methodology to the refurbishment of a case study. So these slides are in Italian because I took some elements from previous presentation. It's just the map of Milan and some visualization of the buildings that are part of my census. The buildings are a lot. The one that I'm taking in consideration is a sample of more or less 100 buildings that represents the general characteristics of all the available building stocks. There is a database with all the information on the buildings, and then I try to construct a matrix of linking the typology of the building, the day, the period of construction of the buildings, together with constructive, typological, and functional organization of those buildings. So I came out with different building types, mainly these 7 categories, and each category can be somehow represented in a schematic way in order to be representative of the whole group. And then each category has a determinate constructive typology, and also linking the localization of those buildings with the city of Milan to understand, for example, in the city center there is a majority of building with a certain characteristic, on the borderies we find other kinds of building, and see if there is a link between the typology of the building and the localization in the city. The localization is important also for the conversion strategy because, for example, in the city center, all the buildings can have a future as office building because it's so strategic being in the city center that also if the building is not compliant with the most, the optimized space plan for an office, it works for a society being in the center. Outside the city, this is not anymore the case. Then the second part, so it's an analysis of many buildings in which this incremental strategy have been used, and some precise example in which they kept the structure of the building, demolished the inside, or in some cases they didn't demolish the inside and they just added the new incremental volumes, for example, giving external spaces to the office, or adding an extra room, or adding services like kitchen, bathrooms, and all those kinds of elements, and so on. So why adaptive reuse strategy with incremental? Of course, it's not the only way, it's the way that I'm exploring incremental surfaces as possible strategy of refurbishment, because somehow it helps in maximizing the effectiveness of the intervention, concentrating all the benefits of the refurbishment in the external without working too much in the internal, in particular from the point of view of the introduction of plans, technical elements, and all the stuff. And more because working on the outside gives 4 different main improvements and benefits: and aesthetical improvements of the building itself, and also a first starting point of for regenerating urban context in which the buildings are inserted. Then spatial and functional improvement, because it helps in adapting the existing floor plan to the new function. Then structure, because the majority of the building that I'm considering reached the end of their life cycle, so they are almost 50 years old buildings, and they need also seismic improvements, and so through the additional elements you can also provide a structural reinforcement of the existing building. And then, of course, it's one of the main aspects in this period, in particular in Italy, is upgrading the energetical behavior of the buildings, minimizing consumption and using also renewable energies. The different, also the ways, but how we locate the new addition on the building. And there are four main strategies. The first one in reality is a subtraction. So we go inside the surface of the existing facade to other exterior elements, and this subtraction, as we will see later, will make you gain some surface that you can locate in other places of the building. Then you can have single addition in specific points, concentrated addition, or diffuse addition all along the entire facade. This principle of the addition, or better, of the equipped facade already existed in many examples of the Milanese historic architecture, modern architecture, because in a specific period of the 90s, many buildings were conceived having the facade as elements for the technical spaces, such as kitchen and toilets, because they helped also in energetic behavior. The building creates a depth of distance between the bedrooms and the external. Now, the second part is starting from here, so from my mobility here. So I jumped in shape grammars, and I thought that that could be a good methodology to, for my purpose, so for the adaptive refurbishment of buildings. In particular, I take shape grammars as an instrument for me to explore preliminary design hypotheses for the adaptive reviews of an office building into housing through the transformation of facade, given a certain system of constraints and the boundary conditions that are both linked to the building itself and also to urbanistic regulation, and so the urban context around the building, and a certain set of design elements that are my incremental models. Moreover, the idea is that, as I showed you before from the census, I found different types of building. So the case study is on one of the types of the building that I'll show you later, and the idea of parameterize the dimension of the buildings, and so to find an abstract schema that corresponds more or less to all the buildings of that category can allow to find a methodology and strategy that can be then applied to all the kind of refurbishment linked to that particular building schema. And also, once set out the methodology, can be shape grammars can help in finding out a sort of transformability capacity of the building itself. So to help public administration owners and etc., all the real estate investors to understand, given a specific building, its capacity of being adapted to residential reuse. So the process that I'm trying to follow is divided into 4 steps. The analysis step, in which there is the analysis and comprehension of the building that I'm working on. And all of those steps have an output. So from the analysis aspect, the output can be summarized in representation. That is to say, finding different forms of description of the initial building in terms of morphological, functional, relational, structural, technological characteristics of the building itself. Then the formulation process is the one that helps in the identification of the ideal transformation strategy for those general schema of building, and from the formulation process, the idea is coming out with a rehabilitation pattern, that is the identification of different levels of grammar that already take into consideration certain boundary conditions. Then the design process itself that helps in the declination of the ideal rehabilitation pattern into the specific building I'm working in through the definition of rule settings and different sequence of derivations of those rule settings. And finally, what I was talking about, a sort of evaluation phase in which finding out indicators of the capability of transformation of a specific building. The case study I decided to work on is this building, because when I have just a few months for develop, so I will not develop a full grammar for but it's more a methodological framework, and then in the future work can be implemented. This building is a building together with the PhD I used to practice architecture in office, and one of the projects that I followed was the rehabilitation of an office building into housing. So it's a case, but I already worked on that. So I started to see from that building which were the rules we followed, and try to figure out the general strategy adopted, and then try to make this strategy abstract and apply to the schema of the building. So this was an office building, particularly in the city center. We made different proposals for the different floors. So dividing the floor some way on the lower floor, we had more apartments, 5 apartments per floor. Then going up, we had 4 apartments per floor. And then on the last floors, we had just 2 penthouses. So it was also for each floor plan. So I had already different kinds of floor plan already developed. This is one example. And so I concentrated on the study of these 3 main floor plan that we developed. In reality, there is one more floor plan that I have to analyze, that is with 6 dwellings per floor. So the main differences between the first 2, that are both with 4 dwellings per floor, but in one case we had the night zone at the corner of the building, and in the other case, so on those sides, and we see later, and in the other case we had the day zone on the corner. And just this difference is make me think rules for generalize later the organization of the floor plan itself. And then there was the plan with 5 dwellings per floor. So first, I tried to figure out an abstract schema for this building. So there is the shape of the floor plan and the shape of the core that is in this case exactly in the middle, as many kind of buildings of this category, that is the tower building. Then I started to study the entry points. In the first 2 cases, directly from the core, we had 4 entry points. In the last case, where we had 5 dwellings per floor, we have 4 in this case. And in this case, there were 5. I repeated 3 twice, but for 5 different entry points. Then I started to understand the circulation schema. The idea of circulation could have been all around the staircase, but in order not to waste space, we had just these additional spaces for circulation for entering inside the dwelling. And after the circulation schema, I figure out the division into dwelling for each floor. So in these first 2 cases, 4 dwellings. In this other case, we divided the floor plan into 5 dwellings. This is not working, this schema. I made it, but then I'll show you that it's not the correct representation. I tried to understand which was the internal circulation of the different dwellings, but those schemas are not really, I don't think, are correct representation of the organization, internal organization of the dwelling. And here is the representation of the division of each dwelling into day area, that is the green one, night area, that is the yellow one, and service area, that is the gray one. The interesting thing is that, as I was anticipated before, between these 2 schemas, the difference is in fact the position of the day in the central area in the first case, and the day area on the corner side in the second case. In day area in Italy, we normally include living, dining, and also kitchen, because kitchen is really linked to the everyday life, and often we are not having any more separate kitchen, but we are making use, while in the night area are all the bedrooms, and service areas are toilet, closet, storage, and bathrooms. Then after the day, the zone division, I entered into the room division. So identify the different rooms, living, dining, kitchen, studio, single bedroom, double bedroom, walk-in closet, and the service areas. And after that, in the real practice, we started introducing, as it was a building office, it doesn't have any external areas, so we introduced lodges just on the south facade. And then we saw that was necessary also, and we could, according to urbanistic rules, also extend all the building. And so we made this extension all around, and was 2 meters all around the building. This theoretical extension then has been characterized with internal areas, external areas, and technical space. So what is in pink were internal areas that then we assigned to different zone division, and what remains in gray were the balconies that were added all around the building. So as you see, starting from the inside organization, the internal area in the addition took the same function of the corresponding zone, and also in the going on in the room division. So they became like the extension of initial minimum dimension of the room. In some cases, for example, in this one, this was a single bedroom, and thanks to the addition, this apartment gained, for example, two double bedrooms. And so in this, we use extensions and incremental surfaces just to extend already organized dwelling. So having studied this case, I figured out my abstract methodological schema for the shape grammar application. And in particular, I understood that I need, for my purpose, different levels of grammar. The first operation was defining the initial building, because I wasn't interested in the demolition of all the internal partitions. So I decided to use as initial building already the clean floor plan with structure and staircase. That was what we kept also in the practice for the building. Then the first level of grammar that I need to define is a definition of the division into dwelling. That for me is one of the most interesting element also to understand the transformation capability of a building, and also oriented to the market to understand that building, how many different strategy of conversion can have. Then is the second level of grammar is the definition of the internal organization of dwelling, and the third level of grammar was is and will be, in particular, the definition of the facade addition and the way of organized facade addition around the building. Because the final aim, the final results that I'm looking for, in reality, is the definition of the facade grammar. So it's understanding the internal organization and the external addition that I will introduce, which kind of facade grammar will generate for my building. So those levels are not in a linear sequence, are open levels, because they start from the first two, from an inside to outside approach, while the last one is starting from the outside to the inside, because I saw during the analysis of the already done experience that the addition then simply took the function that was already given during the design phase, while starting from the external gives different possibility of internal organization of the building itself. So facade grammar will be the result of initial data that are both linked to boundary conditions that are external to the building, for example, urbanistic regulation, because to go out to the building, I need to follow the rules of the specific context, the orientation of the building, etc., together with the building data itself. And in this case, to simplify the result, the facade grammar will be the combination of the results coming from both approaches. The facade grammar could also have combined together the two series of results. Okay, first step was defining the initial building. So starting from the initial existing floor plan, I came out with a an existing building simplified plan after the demolition, and the scheme of that plan that considers the floor area, the core area, and the orientation points. Then the idea is create a parameterization of the building type, because in other case I can have a bigger building with a bigger core, and so if I find a way of making it an abstract and applicable to different situation case, I can find a methodology that can be easily used for other buildings of the same kind. The initial building, as I was saying before, needs to be described in different ways. One way is the one that highlights the structural elements of the buildings. The other is the plan simply after the demolition. Then I need to figure out which are the different areas that are later labeled as usable area for the new dwellings, the stair areas, the elevators, and the circulation that is important then to understand the division into dwelling for each floor. And then the last schema is the representation of the spatial relation between the core and the usable surface. This kind of representation were already used and experimented from Sarah Loy during her PhD thesis that was about the refurbishment of Rabo de Bacalhau building into new contemporary dwellings. So starting from the inside to outside approach, the first thing was defining entry points. And so in this case, according to the dimension of the circulation area, it's possible maximum to have 6 entry points. Then starting from the entry points is find ways of figuring out circulation patterns that are strictly linked to the number of dwellings that we want to have on a single floor plan. As a matter of fact, if we need bigger apartments, we don't need to have much circulation because they can be all accessible directly from the staircase. If we need a bigger number of apartments of smaller dimension, in this case, we will have to add circulation. So this is the general framework. In parallel, I started developing already the grammar for that, but I'm not presenting it now, but I would like to discuss it with someone as soon as we can. So starting after the circulation schema, there is the important aim of defining the division into dwelling. For that, I decided to use 2 parameters, starting from the Milan regulations and also the last experience of new social housing in the city. The range of buildings that I saw and the typology that are requested by the market are from a minimum surface of 28 square meters to a maximum surface of, in reality, I move it to 140 meters, dividing dwelling from the studio flat to the 3-bedroom apartments. And also the minimal dimension of dwelling is linked to the orientation, for example, because on the north side you cannot have a bigger dwelling, and so I tried to include all the constraints that were linked to the dimension of dwellings and the position of dwellings. And for example, simply starting from one dwelling, I was trying to figure out the possible subdivisions and the implication of the subdivisions then on the circulation patterns. Second level is, once that you define the dwellings for each floor, is starting with the internal circulation schema. I was testing the simple scheme of the corridor circulation, but what I think that in reality is not the way in which contemporary dwellings are always organized. And so we should think also other kinds of circulation. But for this purpose, to simplify, the 3 main internal circulation I defined was the rear corridor, having the middle corridor parallel to the horizontal extension of the building, of the dwelling, and the middle corridor in a vertical position. And then I started giving parameters for that. For example, I know that the minimum weight for a corridor is 1.20 meters. So if you know this dimension, then you know, because it's an existing building, the other dimension, so you can start creating rules that also are linked in a parametric way to the dimension of the building. After the circulation schema, there is the definition of the internal zone in day-night zone, and divided according to the different circulation schema can be organized in many different ways. And then the division into rooms, and also in this case, this data starts from the Milan construction regulation and the health and care regulation, national regulation, but it's important to have the minimum requirements by law and also the plus. In case we have more space, this should be ideal dimension for having a more optimized floor plan. And then there are some constraints always linked to regulations in Italy. And so I tried with these two parameters, so with the zoning and the division into dwelling, to make a simplified derivation to see, for example, the different steps that will help me in the formulation of specific rules for adding surface, dividing surface, and starting from the day and night division into more detailed schema that will bring to the final floor plan. Starting from the outside and going to the inside, it's the other operation that I would like to explore. First of all, where I find the incremental surface, there are two different main ways. The first one is the energetic bonus in Italy. That is to say, if you make energetic savings for the building, you can gain the 5% of additional surface that you can add all over the building. And for sure, as we are redoing completely the facade, the incremental of energetic behavior will be sure after the intervention. So we gain this surface. And then you can gain surface if you cut new lodges on the floor plan. That is surface that you can allocate in other places in order to add the function that you need. And so the total amount of additional incremental surface can be organized on the floor plan in many different ways. For example, you can divide the total amount in equal way on all the floors, or you can say that the lower floor will not gain that surface and you will give the surface only in a crescent way or in the crescent way. So there can be many different patterns for allocating this surface that I really still need to develop more this part. So for example, if I go all around, and so I need to take into consideration for the outside to inside pattern two levels, the building level, so the total amount of surface along all the building, and also the dwelling level, so understanding how to make interact the new surface with the future new dwelling. For example, just to make a simulation, in this building, if I use all the surface that I need, simply filling 2 floors, something that could be a possible operation, I will need just, for example, all built surface around 2 floors plus other 66 square meters to fill all the new surface. Or if I want to divide the surface from the floor 3 to the 11th, I can have 60 square meters for each floor that can be distributed in different ways. From a dwelling level, for example, one rule can be linked to the position of the pillars, because if we have an addition in a strange position with a pillar, for example, we cannot enter in the addition. So the two possible way of locating the new addition can be or between 2 pillars or having the pillar in the middle so that you can pass from both sides. For example, one possible rule for locating these surface. The other important rule that I'm not introduced is following the orientation, because I will not go out on all facade in the same way, because maybe on north side you can go out in a certain direction with a certain proportion, while from the south you cannot. In this specific building, for example, there was urbanistic rules that allows going out only on 2 of the 4 sides. So for this case, one of the constraints will be this urbanistic regulation. And then also assign the function to this location that can be of 3 types. One that are internal incremental spaces for the expansion of room surface for adding new kitchen or new bathroom, and the other can be external incremental areas for creating bioclimatic greenhouse, lodges, or balconies. And finally, can be also external addition to provide technical space to the building that are, for example, a double skin facade, the addition of the insulation, the external insulation, or technical area for the passage of implantation ducts and that stuff. Developing these two approaches, the idea is getting to the facade grammar that should derive from the combination of the two approaches in order to give you a quick feedback on the way in which the transformation that you propose on the floor plan will affect the general transformation of the building. What? The grammar already? No, now I don't. I can have something. I developed just the grammar for the division into dwelling of a floor plan, but I have and drawn.
One question here. This last part of the grammar, may I use, let's say, evaluating the transformability. You said that you would be also defining some indicators to
that could be
used to did you think about the indicators?
No, the idea is that I imagine that this can give indicators to a person that has a building, so to test quickly with the dimension of the building if he wants to transform the building with studios or with 2 or 3 bedrooms apartments, and also the constraints of the plans in terms of proportion of the plans, how many dwellings it's easy to locate. So as if you develop it in a future parametric way, you can have a software that's combining the data of the number of dwellings that you want to have and can give you different scenarios for the transformation of the dwelling in terms of feasibility. This can also provide the indicator for the flexibility of a building to be converted into a specific kind of function. No.
A few comments. First of all, I think the word is very, very interesting. And it's very well structured. So it has a lot of potential. I would say it's coming close to an end. Still, I remember that when I was doing my PhD in Delft, I saw a presentation exactly about some buildings retrofitting, and one of the strategies was extending the building towards the outside to make it basically to enable the possibility of controlling the environment in that way, and also that was also a strategy for building urbanization in the sense that you would get higher value, property value out of that dimension. I think it was published, and I probably have something.
Yes, I have many references from Delft School on these studies. Maybe I'll show you if it's the same kind of study. It's Remoy, the name.
I saw there were people from Delft in this presentation, but I saw it in a seminar in Albania. It was a particular situation. I'll check if I have, because there was a publication on this. Still, few comments. First comment is that the presentation is very easy to follow, very nicely structured, so we understand everything, no doubt. And it's also very nice to see in the sense that the graphics are very, on one hand, standardized, so we can always understand the same things, and they also look nice because colors are conscious. Not just meaningful,
yes,
beautiful. So all these are, I would say, qualities. I think, of course, this is the last part of the work, the development of the indicators. And I would say that the main use of the indicators would be to really have an implementation of adjacency. You could have a real tool that would allow you to very easily test several solutions and information to promoters, and that's very useful, very interesting. Did you look into those ideas from the support theory from John Abraham?
Yes.
Okay.
Yes.
I thought
yeah.
would do it. Because there's obviously a quite good relation with using the bands as the
structure.
Structuring the project, what he calls zones.
Yes.
Good. I would be just curious about how you would define the indicators, because some are reasonably obvious, like the amount of area that you gain, what percentage of area that you gain. But then there are other issues like the cost of intervention. Yeah, I don't have much more to say.
Thanks a lot.
One thing I have to say is that I have a lot of stuff to do, and I love these presentations. These meetings are really important. These are the moments where we all learn a lot. And every time we do a presentation on this kind of meetings, everyone gets some information that will be there and
All who wants to present, they just come and present. This discussion gives you about.
There was a time this was really even more.
Yeah. Lately we slowed down for several reasons, but still, I agree with this. One comment, not exactly for the new, but because some of the examples that we show actually can give you some ideas on what I was talking about. So organization comes from the supports to Abraham. This is one thing, but also the first plans. Can you get back to the first plans that you showed about the first design that you took as example?
The last one? This?
The first one. It's actually the first plans that you showed. Yeah. This. Yeah. These three plans, which correspond to the three levels.
Yes.
They actually respect all those aspects that I told you about when I was saying about having a kind of a layer that is structured, not just the structural matrix, but also the composition. You have both things there, and it's very, very clear. Okay, you immediately spot an order. Tell you, can you tell me where the structure is? Can you tell me where the compositional rules are? Can you read it? Usually, with architectural project has that.
it's immediately kind of jumps to your eyes. So this is something that architects always try to define as a first layer of constraint. So try to figure out if there is any way, of setting out the system in a way that you can have this layer order. Because it really brings different outcomes.
Can I ask you something? Because as now Professor Duarte was following me in this development, and now he's not anymore very close, so I don't think we'll have many occasions of comparing with him. I really don't know how, because I developed just the first part of grammar about the division into dwelling of the floor plan, but I would like really to show to somebody, to discuss a little, also because this is the general framework, and I don't think that in my case the main idea is really developing all the levels of grammar, but was more a general overview, and maybe the most interesting part can be figuring out indicators that are, this is the last chapter of my thesis, that can be really like the future work to be done. But still I would need to speak with somebody.
Yeah, well, we can schedule a conversation on this. And what I would say is that you first bring me all the information you have in terms of the development of the grammar. In any case, during the presentation, it's very easy to understand that there is already some grammar.
Yes, that's the thing that Professor Duarte told me, and I tried for the division into dwelling, that for me is very crucial to do it, but I would like to show and discuss about that, because doing really, and for me the difficult was also trying to find mathematical way also of setting boundary condition, and also the graphs that helps in understanding, because I would like to find like a generic way of really creating the floor plan. I mean, in particular, the division into dwelling. I don't mind organizing inside the dwelling, because it would focus more than on the additional element parts. But just to have a talk about that, and the first rules that I try to sketch could be. Yeah. When I don't know if to you or to Professor Romao, to have somebody.
Yeah, I mean, you can also talk to Professor. Still, the main thing is first to divide it into those different levels of parameters. I think that makes a lot of sense. For me, it's absolutely correct. Then there was a moment in some slide that I thought about that some of the order is being lost at a certain step. Then somehow you recovered that order. Maybe by checking all the rules, you can see if there's some step that could be improved. But the main idea is that was to have these 4 levels, and to identify the rules of the grammar for the several levels. The first level is probably the one easy to define, with the grammar definition. The second level is not the most important for your goal, but it's the most difficult one. And the only thing that is important in that level is that it constrains the facade definition.
Yeah.
So I would say that basically to solve the second level, following some of the solutions that Sari developed for grammar is probably correct. But in any case, the apartment structure of the technology is a bit more complicated.
Yes, because all the internal part that you cannot demolish. So in my case, it's completely different because it's more like doing a completely brand new design. I have less constraints than in our case.
Also, by following the zone logic from and probably makes it a lot easier to define basically the topology. Okay? Because what Sarah used to, let's say, control the housing program is basically the graph.
Yeah.
The graph establishes the relations and keeps the program in a logical way. As soon as you have the zone system, you already have some embedded order in that.
Yeah.
And it makes it easier to control the graph. But it can be approached in more or less the same way. Yeah. But we can check that step by step.
Okay.
That's the most complex part of the grammar. But it also has this funny thing, it's the most complex, but it's the less important.
Yeah.
Still, it adds some information in terms of let's say, the cost of the intervention.
It's more.
Some information in terms of the extent of the intervention, the amount of construction effort.
Exactly.
And when you, at the end, evaluate with some indicators, I would say that a few of the indicators will have to do some attention on this topic of construction.
Yes, that's for sure.
But the most important thing is to actually really have a tool that very easily will help you, give this information to the stakeholders. That's a strong added value. And gives you a competitive advantage. Yeah.
In the beginning, I was wondering about the regulation of the municipality. How can you increase the square footage of the building so much? Because just by going a little bit further outer of the origin of the site, you're already giving so much area to the square footage. How can you do it there? How is it possible? But then you already refine it with these models.
Yes.
Of the
energetic behavior.
So basically, you're proposing
speculation. No.
Because we're going to solve it. It's like, first of all, you're taking advantage of the models, and then with the solution, you provide the reason to the models. And I don't know if you're one of the characteristics of your project / grammar in the end will be to evaluate how much the gain in energetic efficiency is going to be or not.
And we are really calculating that. No, what I'm doing, what I did with the benchmark, and I will systemize, is that I found data of similar intervention done in other countries, in European countries. So I have the values of certain kind of intervention in terms of eco-energetic behavior. So what I can introduce in the indicator is already where the benefits in other building already realized, that where after there is a very nice program in Germany that monitors the building after the energetic behavior intervention for a certain period. That is optimized building. If you want, I can give you the link. And so with those data, I can know if I made, for example, an external insulation, if I expand the facade using a particular technology, which will be the benefits in terms, which were in those cases.
You can simulate.
Yeah.
But in the end, after you grab the solution, you can always send it to an evaluation
Yes.
And with the graph, we can also, maybe one of the interesting things would be to make provide a universe of possible solutions, and then just evaluate.
In terms of energetic behavior.
Okay, this would give higher rents.
No, in fact, the idea of understanding the different scenarios of transformation of the building is to evaluate also from an investor point of view the scenarios. And also it depends, for example, in this real practice case, we started with this investor, then the project never really started because of financing, bank problems. And as usual, but that's a kind of stakeholder needed specific targets of dwelling, so we prepare for in those dwelling. Then after 4 years, we saw that another office got that project, was another stakeholder that really took the building, and the program was completely different. So it's also that with the same building you can propose, if for example it's a public building, a municipality, that the problem is that it's an abandoned building that is just a cost in terms of also contexts that are not anymore, that are not well preserved in terms of energetic behavior and all the stuff. A municipality can propose the same building to different kind of stakeholders because can evaluate previously quickly the different scenarios that that for a stakeholder implies different business plans for really taking the building and developing the strategy of conversion.
Picking up on what you were saying about the regulations, and probably the Portuguese regulations really go out these type of extensions towards this theory. I would say that this simply shows that the Italians as well as the Dutch are obviously further ahead in terms of the development.
Also the law, that's true.
I'm not sure, but there is a reasonable, it is reasonably accepted already that transformations on the facade can really transform the building behavior.
Yeah.
And so interventions that consider only the inner spaces of the building are less liable to produce good results in terms of energetic behavior of the building, while reasonably simple or technologically simple interventions just considering the scheme of the building will create
a lot of benefits.
So if you can have this tool also as a measurement, can provide real reliable information on this kind of topics towards a municipality, I would say that our law has a typical problem that is over-constrained in many aspects. You always need to decide on what are the laws that you're not going to fulfill, okay? This happens in every project. And as soon as this is true, it means that you can actually choose the laws that you are not going to comply with. And you simply need to explain in every detail why you don't do it, okay? So sometimes you can have enough information to actually start with some design problem, with some stakeholder that is willing to take the risk, and start with the negotiation process with the municipality. And this is possible.
Just by starting saying we are not going to comply with that.
Yeah, but showing evidence, okay, that there is an advantage in not doing so. Laws are not necessarily correct. Laws are there because at a certain point somebody made them up based on some criteria. And even the criteria that was used at
in the
that
past
time might have changed.
That's true.
And that's enough to make a law that was right at a certain point become obsolete at a certain point. There are always laws that are obsolete, and we have to cope with that. And creating evidence that they're not correct is providing opportunities for change. And people will start accepting exceptions on the basis of evidence, and even, you know, simply delete the law.
Yes,
Change something. It happens.
Yes,
it's always happening. It's constantly. I would say that actually the evolution of the law is the deleting process and not the addition process. Because the addition tends to over-constrain and create problems, and deleting tends to freedom and options.
And opportunities.
And if goals are still kept as target issues, it's the most important. That also has something to do with the practice of the law. There are some countries that are able, with that practice, to keep the spirit of the law more than
the really strict respect.
Detail. Anyway, I think that's also a change. There was at a certain point during the last conversation, I remember that there was one statement at the beginning of the presentation that I really didn't agree with.
Okay.
And that was when we were talking about you know, the buildings in the center have always the potential to be recovered
to offices.
To offices. Somehow that is true, but there's also the implication that, okay, outside everything has to be residential.
Right.
And there are also some planning issues in terms of, and now I'm speaking on a planning scale, which is another thing. And it should be always thought at the regional scale, especially because the region of Milan is really big and very dispersed.
Yes.
So it means that in that region, planning needs to understand where are certain spots to create new centers and intensify those centers. Especially in a city with more than 1 million inhabitants. I'm thinking of the city as a metropolitan area. From 1 million inhabitants above, it needs to be
polycentric.
Otherwise,
Milan is already polycentric.
In the case of Milan, the polycentric strategy is clearly something that needs to be done. So it's not as necessarily or exactly as you said, although there is some.
No, I was saying yes. In terms of in those cases, you can evaluate if keeping the office or converting anyway into residential. While other buildings for sure will not have any future as offices. In those cases, one possibility can be also keeping the function of office, also if the building is not compliant with the most common requirements for offices.
There is also the mixed use.
The mixed use. Yes. Okay, thank you very much.
No, so thank you everyone for attending this DCG lecture. As we have been sending the information to everyone in the list, the video of this session is available in the DCG Hangouts. And well, hope to hear more from you and looking for future sessions. Thank you.